So, what if you had to scan millions, maybe even billions of data points and instantly find the ones that matter the most? Well, that's the heart of the top K problem. And today, we're going to pit two legendary algorithms against each other in a head to head battle to see exactly how it's done. Okay, let's get into it. All right, picture this. This is your job right now. A massive, totally unsorted list of 10 million numbers flashes in front of you. You got to find the top 10. You can't just sort the whole thing, that would take way too long. You need a smarter, much faster way to just pluck out the winners. And believe me, this isn't some theoretical puzzle. It's a real challenge that systems we use every single day have to solve. So here's the official name for it, the top K elements problem. The idea is, given a huge collection of N items, you need to efficiently find the K items that have the highest values. Now, K could be 10, it could be 1,000, but the key is that it's usually way, way smaller than the total number of items, N. And look, this isn't just some abstract computer science problem. This is the real deal. Every time you see a top 10 list on a gaming leaderboard, or get a product recommendation on a shopping site, or even see the most relevant search results, yep, a top K algorithm is humming away behind the scenes. It's one of the absolute fundamental building blocks of modern data processing. Okay, so how do we actually solve this thing efficiently? We're going to look at two classic battle-tested champions from the world of algorithms. So let's meet our contenders. In one corner, we have the heap method. Think of it as the steady, reliable pro. It's fantastic at handling data as it comes in piece by piece. And in the other corner, we have the quick select method. This one's the speed demon. Lightning fast on average, super aggressive, and just built for raw speed. Both are brilliant, for sure, but they have totally different ways of getting the job done. And you know, these aren't some new kids on the block. The core ideas for both of our contenders were actually developed way back in the 1960s. QuickSelect's foundation was laid by the legendary Tony Hoare in 1961, and the heap data structure was introduced just a few years later. The fact that we're still talking about them today tells you they've stood the test of time. First up to the plate, let's break down this strategy for our first contender, the heap method. Its approach is really elegant, but it has this super clever twist that honestly catches a lot of people by surprise. Okay, now here's where a lot of people get tripped up. It's a really common trap. Your first instinct is probably, okay, I want the largest items, so I should use a data structure that always keeps track of the maximum element, a max heap, right? It seems totally logical, but it's actually not the most efficient way to go. And boom, here's the plot twist. To find the top K largest items, you actually use a min heap. Yeah, you heard that right. A data structure that's specifically designed to give you the smallest element. I know it sounds completely backward, but this little counterintuitive trick is the secret to the heap method's efficiency. Let me show you how it works. Okay, think of it like this. You've got a conveyor belt with millions of numbers rolling past you. You're only allowed to keep, say, 10 items in a special box on your table. That box, that's our min heap. So for the first 10 items that come along, you just toss them in the box. But from then on, for every single new number that arrives, you only have to ask one simple question. Is this new number bigger than the smallest number I'm currently holding in my box? If the answer is yes, you kick out that smallest one and put the new, bigger one in. If it's not bigger, you just ignore it and let it roll on by. You see what happens? By the end of the conveyor belt, your box naturally contains the 10 biggest items you've seen the whole time. Pretty cool, right? So what does this all add up to in practice? Well, it means you get very predictable, very reliable performance. We look at each of the N items one time, and for each one, the hardest work we ever have to do is a tiny update to our small heap of size K, which takes what we call log K time. It's steady, it's dependable, and it only needs enough memory to hold those K items. All right, that was the heap method. Now let's turn to our second contender, quick select. If the heap method is all about steady, careful filtering, quick select is about aggressive, brute force division and conquest. The entire game for quick select comes down to one core operation. It's called partitioning. Here's the idea. You just pick one random element from your collection, we'll call it the pivot, and then in a single pass, you rearrange the entire collection so that everything smaller than the pivot is on one side and everything larger is on the other. It's literally like drawing a line in the sand. So here's the play-by-play. You pick that random pivot and you draw your dividing line. Then you just check where it landed. You ask, if this data were sorted, would my pivot be in the exact spot that separates the top K items from everything else? If the answer is somehow yes, congratulations, you're done.
but most of the time it won't be. Let's say your pivot landed too far to the left. Well, now you know for a fact that the real answer has to be somewhere on the right side of the line, so you can completely ignore the entire left half of the data and just repeat the whole process on a much, much smaller piece. You just keep dividing and conquering until you find that exact spot.
And the payoff for this aggressive strategy is, well, it's speed, blazing fast speed. Because you're potentially throwing away huge chunks of the data at each step, this approach is incredibly fast. On average, its performance is linear, or what we call O of n. That basically means the time it takes is directly proportional to the number of items. You can't really get any faster than that, since you have to at least look at every item once.
All right, we've seen both strategies in action. We've got the heat method's steady filtering versus QuickSelect's aggressive partitioning. Now it's time to put them head-to-head and look at the hard numbers. Let's see the final scorecard.
This is the question that really matters, right? If you have to actually build this thing in the real world, which champion do you put your money on? The answer, as it so often is in computer science, is, well, it depends. Let's see what it depends on.
This table pretty much tells the whole story. When it comes to average speed, QuickSelect is the undisputed champion with that ON time. It's a clear winner. It also wins on space, using practically no extra memory at all. But, and this is a big but, look at the worst case time. QuickSelect can, in theory, degrade to a sluggish ON squared performance. The heat method, on the other hand, gives you a guarantee. It never gets worse than ON log K.
And if you're a visual person, this chart makes that average speed difference crystal clear. If you just naively sorted the whole collection to find the top K, that would be the slowest by a long shot. The heat method is a huge improvement over that. But on average, man, QuickSelect is just in a league of its own. It's the clear winner for raw, typical case speed.
But there's always a catch, right? It is so important to understand QuickSelect's one big weakness, its Achilles heel. If you get incredibly unlucky with your random pivots, like if you keep picking the smallest or the largest element over and over, that whole divide and conquer strategy just falls apart. You end up barely shrinking the problem in each step, and that leads to that terrible quadratic performance. Now, it's really rare, but it can happen. So, we have all the data. We know the strengths, we know the weaknesses. So, how do you make the final call? Let's lay out the practical guidelines for choosing your champion for the job.
The decision really just boils down to your specific needs. If you're dealing with a continuous stream of data that never ends, or if K is really small compared to N, the heat method is perfect. It's simple, it's reliable. If all you care about is the absolute fastest average time and using as little memory as possible, QuickSelect is your go-to, no question. And finally, if you're in a critical situation where a surprise slowdown would be a disaster, think real-time systems, you'd use a more complex, specialized version of QuickSelect that has a safety net built in to guarantee it never hits that worst-case scenario.
So there you have it. You now know the critical trade-offs between two of the most powerful selection algorithms out there. Finding the top K largest values is a solved problem. But what happens when the challenge changes just a little bit? What if instead you need to find the K most frequently occurring items? Well, that's a whole new battle for another day.